Right now, we are going to have a time slot of IFIMUP, Institute of Material Physics and Nanotechnology, and it's a long name. Professor João Pedro Araújo will say the name. I don't want to take time from his talk. So we will have four talks, one introductory one by Professor João Pedro, who is already sharing his screen, amazing. And then 3 talks more scientific so that you know what is the research being carried out at IFIMUP. So with this, I'll give the floor to Professor João.
So are you listening or not?
Yeah, perfectly. Listening and we can see the screen. Yeah, go ahead.
Okay, sorry. Again. So good afternoon, everybody. It's really a great pleasure for me to be with you today, and I would like to start for thanking the organizers to invite me to introduce our institute at University of Porto. And as Sophia already said, is a long name. It's the Institute of Physics for Advanced Materials, Nanotechnology and Photonics here at University of Porto. And I would like also to congratulate all the organization for such a nice event and competition. So it's great to be with you this afternoon. I will give you, it's going to be a brief introduction to our institute, and I will start with an institutional overview, meaning that I will give you the timeline of our historical timeline. We were founded in 1987 here. I highlight in this timeline the major years where we received funding, which allowed to renew or enlarge our experimental facilities. And so only highlighting the most recent ones, in 2018, we led a network of extreme conditions laboratories in Portugal, receiving a funding of around 3 million euros. And this, of course, gave us an edge to perform, to receive new facilities, new state-of-the-art facilities for materials characterization and solid-state physics research. And also in 2020, as research unit, we received the so-called Science Foundation, the Portuguese Science Foundation Evaluation of Excellence, allowing the next 4 years 2 million euro research fund, which we use to perform our mission. So our mission is to perform research, advanced training and services to the scientific community and industry. And of course, we want to enhance knowledge in the fields of functional materials, nanotechnology and photonics. We envision ourselves as an interdisciplinary and multidisciplinary institute of excellence with high international impact on research and innovation, to perform cutting-edge advanced research and training in the areas of fundamental and applied physics. And of course, we would like to have with us the best students and the best researchers, so it's an opportunity for us to advertise to you. In terms of highlights of the recent years, we are able to generate 4 spin-offs. I quote here 9 patents that are related with these spin-offs, and here are also research and innovation awards given to the members of the institute that constituted these companies, which were already able to secure an investment of more than 1 million euros. Concerning research, our institute organized itself for the next 4 years in major 4 research vectors. So one on quantum materials, the second one on advanced energy materials, vibrational and ultrafast laser spectroscopy for biomedicine, and as transversal to all of this, of course, physics education and dissemination. I will go very fast on these three research vectors. So on the first, what do? We want to develop strongly correlated systems that have degrees of freedom that are interconnected, like ferromagnetic materials, which are also ferroelectric, and within the framework of controlling quantum degrees of freedom. Also, of course, nowadays, the development of low-dimensional electronic or magnetic systems, so two-dimensional, and to use them to develop ultra-fast pulse devices using, for instance, high conversion nonlinear third harmonic generation on van der Waals materials or graphene. As a recent highlight on this type of materials, I quote here the development of what they call a phase inverter for spin wave logics and magnonics as a way to control quantum information. And in the research vector of advanced energy materials, we want to develop disruptive technologies to harvest environmental energy in remote and harsh conditions using, for instance, triboelectric and thermoelectric nanomaterials. I think you will hear a talk this afternoon. Also to develop new generation solar cells, namely the ones with tunable plasmonic and magnetic plasmonic materials to enhance performance. As an highlight, I quote here the ability to perform energy harvesting in harsh environments up to 800 bar pressure, and as for instance, this development of a triboelectric nano generator in an oil environment. Concerning the vibrational and ultrafast laser spectroscopies, what we want to do is to develop new techniques, new spectroscopic techniques to study, for instance, cancer cells and biomarkers, namely using techniques like stimulated Raman spectroscopy, Brill-1 scattering spectroscopies to probe mechanical properties in the gigahertz range, and thus offer new spectral window to study biomechanical processes. Also, we develop broad spectrum and high power fuel cycle lasers down to 7 femtosecond or even lower for real-time and multi-labeled fluorescence lifetime microscopy. As an highlight on this last topic, I quote here the development of a portable ultrafast laser for new biomedical imaging technique. So the invention of a new nonlinear microscopic technique that is able to visualize cells under, for instance, a cancer treatment. This invention was made by a group from IFIMUP and the INL, the International Iberian Nanotechnology Laboratory in Braga, in Portugal. Okay, so as a motto, our institute has minding the future. So we see us as a team of people that is, of course, concerned, and so we mind what is going to come, but we use also our mind to invent new solutions for the future of our planet and our research. I finish my talk with a very recent project that we engaged, which is the so-called LabMet laboratory, so the Laboratory of Physics for Materials and Emergent Technologies, which received very recently the title of associate laboratory, and we are leading this initiative, which is an initiative with 3 major universities, namely the Porto University, University of Minho, and the technical university in Lisbon, so Institute Superior Técnico, and 3 major research units, namely the IFIMUP, ourselves, and the Center of Physics of Universities of Minho and Porto, and CEFEMA at Técnico Lisbon. And with this, we want to have an institute with national coverage, and that joins together the synergies of 3 major research units in physics in Portugal. And why are we doing this? Because we identified synergies and complementaries both in research infrastructures and scientific interest. So we think that this will grant a much improved scientific impact and contribution to public policies. I finished that this institute involves more than 160 people with PhD, so staff members, 30% of which are women. And in all, we are able to have a synergy of 100 PhD students, and in this way, hope to have attraction for new students and new researchers all over the world. So I finish here, thanking you for your attention, and I wish you the best for this event. Thank you very much.
Thank you, Professor João. Thank you so much for introducing IFIMUP. With this, I'd like to give the word to Ana Pires. Are you there, Ana?
Yes. Hello.
Hello?
Hello. Everything is okay? Célia?
Yeah, I can hear you.
Okay. I will share my screen. Sorry.
Perfect. We can see it now.
So
Perfect.
thank you, Célia, so much. Okay. So good afternoon, everyone. Thank you so much for this opportunity. My name is Ana Pires, and I am a researcher at the Faculty of Science in the University of Porto in the Institute of Physics of Advanced Materials, Nanotechnology and Photonics. And today I will present our work regarding the printing of flexible sensors. So in here we have the outline of this presentation. I will start with a brief motivation regarding the Internet of Things, the so-called IoT, and why we want to study and apply our things in the Internet of Things. I will explain what we are doing in the field of the energy harvesting and in the printed flexible sensors. And in the end, I will present the future perspectives. So since the announcement of the Internet of Things in 2012, the number of produced devices increased exponentially. So we believe that in the future, everything will be connected and the communication between the devices will be established without human intervention. So in the IoT area, as you can see in this picture, we'll have several communication nodes that will allow us to monitor specific parameters, achieve the data, and transmit that information to the main unit. So this is the cycle. And we can have these communication nodes applied in several areas, such as in smart homes, in the wearable healthcare, in the military area, and of course, will be very important in the industry 4.0, that is the future. So as you can see in this figure, we have the production of the devices as a function of the years, and that is from Cisco database, and we can estimate that we will reach 50 billion of produced devices in the next year. So of course, we need to power all of these devices, and normally they are powering by drawing electricity from local grids. And this can be a huge problem if we want to apply and charge the devices in remote places, such as, for instance, in the deep ocean or in the mountains. So we need to find new approaches to power all of these devices and create new solutions. So that's why we are investing in energy harvesting solutions. So energy harvesting is the process by which energy is collected by external sources, such as the thermal, the wind, the kinetic, and so on, and convert them to obtaining levels of power. So we can power the device with these sources. And even our human body become an energy harvesting system because we release heat, so we can recover that heat and produce the electricity. So triboelectric and thermoelectric generators are the ones more developed in our research group in the IFIMUP. The triboelectric nanogenerators make use of contact electrification to harvest the surrounding energy. So we have two materials, and we recovered the difference between them in the charge. And regarding the thermoelectric generators, this type of energy harvesting technology makes use of the waste heat and convert it directly into useful energy. And in the particular case of the thermoelectric energy harvesting systems, depending on the type of the charge carriers, we can have two different types of materials, N-type materials or P-type materials. So we can combine these two types of materials to fabricate our final device. And in the literature, and as you can see in this image, we have the N-type material and the P-type material. So in the literature, we can find different thermoelectric device configurations. And depending on their configuration, we can have different different processes to fabricate these devices. So we can find, for instance, configurations like the vertical one, the planar one, the radial, and the origami. So in our research group, two different approaches can be used to produce the thermal energy harvesting systems, such as the photolithography process, or by printing process. Over the years, printing became the low-cost way to economically produce these devices, aligned with the reduction of the manufacturing cost and time. So this is our solution and our investment in printing process. So printing is the process for mass production of image using a master form or a template. So in our department, we mostly use stencil and screen printing manufacturing techniques. However, we can also have other techniques such as inkjet printing, 3D printed, gravure printing, and so on. So in screen printing, as you can see in this figure, is a technique where a mesh is used to transfer the ink onto the substrate. So as you can see, the blade is moved across the screen to fill the opening of the mesh with ink. So that allow us to transfer the ink to the substrate and collect our designs. So in here we have two examples, the planar configuration and the radial configuration. So in here we have the electrical contacts and the thermoelectric stripes. So our proposal for the radial configuration, like this, secures the European project that we have, the ITERM project. So in the ITERM project, the objective is to produce an innovative wireless energy transfer system able to wirelessly recharge the energy storage components used in, for instance, in the CubeSat systems. So the production of the flexible photothermal plasmonic system using the screen printing process is the main goal. And of course, will allow us to achieve the conversion of the photons energy into electrical energy by using the delta T. Regarding the power outputs, so we are talking about device, so we need to also talk about the power outputs. As you can see in this picture, we have the distribution of the several devices concerning their power requirements, and has a motivation. The power outputs of our produced so far flexible devices already can be used to charge some of these devices. Of course, the ultimate goal is to increase even more their power outputs to charge about energy storage. That is another research scientific area in our department. So in the energy storage research area, we mostly work in our department with supercapacitors. And we have 3 different types of supercapacitors: electrochemical AA capacitor, pseudocapacitors, and hybrid supercapacitors that results from the combination of the electrical one and the pseudocapacitors. In all these 3 cases, we have the electrodes and the electrolyte to formulate and build the supercapacitors. And we have different types of materials that we can use. And by using screen printing process, as you can see in this slide, sorry, by using screen printing, we already produce smart textiles with high resolution that in fact already achieves enough output to power, for instance, a blue, as you can see in the video, a blue LED. But if the goal is to produce self-powered systems to power electronic devices anytime, anywhere, the combination of energy harvesting with energy storage, it's the dream. So in our research group, we discovered a new technology able to join both technologies, the harvesting and the storage, and we call thermally chargeable supercapacitors. So in this figure, we have the radial thermally chargeable supercapacitor, one example, and give us our more recent patent in smart textiles. And we can use, for instance, this in wearable textiles applications for sports, healthcare monitoring, and so on. So I hope you feel inspired with what we are developing in our research group in the IFIMUP. And if you want and have some interest, please follow us in social media. And thank you. If you have any question, please ask. Célia?
Thank you so much, Anna. Yeah, we actually have 2 questions on the chat. Himanshu, wait a second. Let me give you permission to unmute. Himanshu, if you want, you can unmute and ask the question directly. And also, João, you can. Are you there, Himanshu?
So I see one question. What is the materials?
She just unmuted.
Ah, sorry.
Yeah. We can hear you.
Yeah. So I wanted to ask for the transferring of the material on the substrate in screen printing, what material did you use as the stencil?
Sorry, what is the question? I don't hear well. You understand, Sophia? I don't.
Yeah, I can repeat. So, what material do you use as a stencil to transfer the material on the substrate?
So, yes, in stencil printing, we use a vinyl mask to create our designs. Basically, the vinyl mask has the design that we want to print. We just covered our design and glue the vinyl mask in the substrate, and after we just spread for instance, the silver ink or another commercial inks, and we after drying remove the vinyl mask, and we get the design. Is the way that we do in stencil printing? So it's a easy way concerning when we compare with the screen printing process. We don't have the screen, we just have the vinyl mask. You understand?
Is it easy to prepare these masks?
So
within the laboratory, or do they take extensive time to be prepared?
So to create these designs, we use AutoCAD, or simply we design our mask in PowerPoint. However, we need to have a plotter. That is a machine that cuts our design directly in the vinyl material. But we also, for instance, in the case of the screen printing, need to create our screens. So we need to have, for instance, a photopolymer to expose our mask, for instance. And so it can be an easy way if you want to try just to see if you can print your ink. You can try stencil printing because it's more easy than screen printing. You have lower steps. and easy steps.
One more question. In the supercapacitors which you have patented, on what material are those supercapacitors printed?
So in the case of the supercapacitors, we are using carbon materials, carbon nanotubes, for instance, and has electrodes and has electrolytes. We are using, for instance, PVA, polyvinyl alcohol, and some polymers that we can easily print it.
Are they printed on the fabric? What is the base material? In the slide, you have printed on a white fabric type material.
Sorry, I don't understand.
In the slide which you showed,
yes,
they were looking as if they were printed on a fabric. Was that fabric or something else?
You are asking if we printed in the textile, just in textile, or
yeah.
So in the case of the thermal chargeable supercapacitors or in supercapacitors, yes, we only use in the textiles. But if you want, you can. But it is our interest, so it's our research area. But you can print it, for instance, in the PAT or in the Captain on. So the configuration will be different, because if you want to print the supercapacitors by using screen printed, you need to think that you need to have a planar configuration, not a vertical one. So in the case of the thermal chargeable supercapacitors, we print the layers over in the top of the textile, but we need to change all the time the textiles, because you want to print the electrodes in both sides. So it's a different configuration, because we use the vertical one. But if you want an easy way to print the supercapacitor, you just need to use the planar configuration and print it in 2D configuration. You understand? For instance, you print the electrodes in the top of the substrate, and in the top of the electrodes, you print the electrolyte. But you have two designers to print the system.
Okay, so I need to.
It was a nice topic.
Thank you, Ivanchu. James, can you quickly ask your question? If not, we need to move on.
Sure. So I asked, how reactive are the materials you wear to oxygen? Because these kind of materials tend to degrade a lot. So I guess I'm really asking, what kind of polymers do you use?
So the PVA, it's not a polymer that reacts so much with the oxygen. In fact, we don't have any change in the supercapacitor cycle when we perform the characterization with the PVA, because we dop the PVA with the acid phosphoric. And it seems that don't change so much with the air, with the presence of the air. In the case of the bismuth telluride that we use in the thermoelectric ones, in the part of thermoelectrics, we can perform encapsulation of the devices to avoid this kind of oxidation and this kind of problems in our device. So if you have a problem with oxygen and with the degradation, we can just perform and encapsulation with, for instance, PAT or something that avoid that degradation. You understand?
Yeah. Cheers. Thanks.
So we need to move on. Thank you, Anna. Thank you so much for your talk. Thank you for your question, James and Himanshu. So right now we have Rui Vilarinho. Rui, are you there?
Yes, hello.
You should be able to share your screen.
Okay.
You're seeing it? Perfect. Go ahead.
Okay. So, good afternoon, everyone. I will talk about the polyurethane materials and functional nanostructures group within IFIMUP. And our research line focuses mainly on improving magnetoelectric and multiferroic materials. So, as a motivation, we want materials that have different functions and they are more versatile. And this versatility comes from many times the cross correlation, the coupling between different physical properties, whether it's size, shape, magnetic, electric, and other properties. And a very specific case, which is very interesting, is the multiferroic case, where you have a ferromagnetic, so you have spins ordered, and then you have also a ferroelectric, which is electric dipoles also ordered. So you have magnetic and polar ordering within the same material. And when you have this, sometimes you can even control them in a cross-coupled way, which means that you can control the magnetization with applied electric field, or you can control the electric polarization with applied magnetic field. And this is called the magnetoelectric coupling. So in very briefly, this is what are the magnetoelectric and multiferroic materials. These materials have applications such as the magnetoelectric RAMs, where you can have magnetic memories, and now using the magnetoelectric coupling, you can switch the states of the magnetic memories using electric field, which consumes much less power, and it's much better for nanotechnology and miniaturization. Also, you can use a different architecture and have a four-state logic memory, where you have the magnetic and the electric orderings to choose from. The problem is these materials are very rare, and it's not often that you find them. And even at room temperature, they are virtually non-existent. So we work a lot with the most well-known and most studied magnetoelectric and multiferroic material, which is terbium manganese. So you have terbium, manganese, and oxygen. You have the manganese, which is magnetic, and it's inside this octahedra of oxygens, and then you have terbium in between. And what happens with this material is interesting because it's magnetically frustrated. So you have different interactions which are ferromagnetic and antiferromagnetic at the same time. And so because the material doesn't know how it wants to order, what happens is that it makes different kinds of ordering that, such as this one, is modulated in space. So you have the spins in one octahedra of the manganese ordered in one direction, and then they rotate from octahedra to octahedra, and they are modulated in space. The good thing about this is that in the case of this cycloidal, this modulation breaks the center of symmetry, which means that you have a ferroelectricity coming from the magnetism, as it's shown here. So because the ferroelectricity comes from the magnetic ordering, they are inherently coupled, and now you have a multiferroic that is also magnetoelectric, which you can control in a cross-coupled way. So just to show you a few results on terbium manganite, which is actually very well studied by many groups, you see that it has a ferroelectric polarization, and it changes as a magnetic field is applied. But the way it changes is not so strong as one might expect. It has an interesting effect which rotates from one direction to the other, but the overall value is actually quite constant. And what we found out in our group is that if you substitute some of these manganese spins by iron spins, the iron spins are much more sensitive to the magnetic field. And now when you put 1, 2, or 4% of iron, it's enough that it becomes so sensitive to the applied magnetic field that you can actually turn on and off the electric polarization at low temperatures using somewhat high magnetic fields. Another way to explore magnetic materials and multiferroic materials is, for instance, using gadolinium manganite. So gadolinium manganite is like a parent of terbium manganite. It's very similar, but it's not multiferroic. It becomes multiferroic if you apply 2 Tesla of a magnetic field. And this is because gadolinium is larger, and these interactions between antiferromagnetic and ferromagnetic are a little bit different, in a way that you end up with this sinusoidal collinear magnetic phase, which does not break center of symmetry, so you don't have a ferroelectric polarization. Anyway, we can play with this material as well. We can now substitute some of this gadolinium by yttrium, and yttrium is smaller, and then you, in average, will increase these angles, such as and obtain the same angles that you have in terbium manganite. So you can take a material that is not multiferroic and make it multiferroic by substituting some atoms. And showing the results for this, you obtain this cycloidal again. So in gadolinium manganite, where this X is the yttrium concentration is 0, you have no ferroelectric polarization until you apply 3 Tesla, as I've said before. And if you have 10% of yttrium, nothing changes. But if you have 30% of yttrium, now you have ferroelectricity even without applying a magnetic field. So you use the atomic substitution. So now you don't have to apply a magnetic field. And then if you apply a magnetic field, the polarization actually increases and you have a large positive magnetoelectric coupling. So it's a magnetoelectric multiferroic material, let's say made by design. And this is just its phase diagram, where here you have a ferromagnetic phase, and then you have an antiferromagnetic phase, which is ferroelectric. Another way to do this without having to substitute material is using nanotechnology. So you can use strain engineering to use a substrate that will change the gadolinium manganite structure in a way that, again, you have the angles that you desire, so that you have that cycloidal, which is ferroelectric. So the way we did this was we deposit the gadolinium manganite on top of strontium titanate. And for very thin films below 30 nanometers, this strain applied in the interface is sufficient that the gadolinium manganite becomes ferroelectric, as it's shown here. It grows on top of the strontium titanate like this figure shows, and then you have a polarization that appears around 35 Kelvin, and then you have a maximum value. So again, you can make another magnetoelectric multiferroic material, not by atomic substitution, but by strain engineering using nanotechnology. Then there is a new research field that is appearing, and it's appearing in some research groups, and we are also joining this, which is instead of having a multiferroic material, we have a dynamic multiferroicity. And what this means is that we join forces with another group within IFIMUP of ultrafast lasers. And what you do is you take any kind of material, some paraelectric, paramagnetic material, then you apply a terahertz pulse, terahertz because it's a wavelength that is good to make motions of the atoms, and you have a coherent motion of the atom. You move this atom up, this downwards, and you have a local electric field or a local electric polarization. So the material now is ferroelectric. Of course, this material is ferroelectric only for a short duration after this pulse arrives, which is in the picosecond scale. So you have let's say, a transient ferroelectric phase coming from a paraelectric material. But if you want to have dynamic multiferroicity, you have to go further and you have to make magnetism also happen. And the theoretic model behind this, which is now trying to implement both at IFIMUP and with other competitors in other groups throughout the world, is you put a motion of, induce a motion of the atoms along one direction, then you induce a motion of the atoms along another direction using a circular pulse, and then in the end you have a circular motion of these atoms. And as you know, if you have a circular motion of atoms which are actually ions, so they have an electric charge, you create local currents, local spins. So you can generate magnetism from this. So at the same time, you can use one or the other and induce ferroelectricity or ferromagnetism in paramagnetic and paraelectric material, virtually in any kind of materials, and have dynamic multiferroicity for some picoseconds. So this was already tried very recently in 2019, and they tried only the ferroelectric part, which is the easiest, and they used its Terence pump pulse to induce the motion of the atoms in a sample. And then what you do is you send another pulse, which is the probe, and you have some delay. And this probe can show if it's ferroelectric using second harmonic generation technique, or if it's ferromagnetic using magnetical optic carrier effect. And if you change this delay, you can take photographs or frames of what's happening in the material 1, 2, 3, 4 picoseconds after the Terran spun pulse. And as you can see here, this magnitude here relates with the ferroelectricity. It becomes ferroelectric, and then this ferroelectricity disappears with time. So now we have another way to make materials by design, which is using simple high energy and ultra fast electric pulses. So I want to show you, and as a final remarks would be like magnetoelectric multiferroic materials are important. You have nice properties, also important for applications, although most of them for now exist at below room temperature, but they are very rare. And sometimes you can take one of them that you know that works, that nature made in magnetoelectric multiferroic, and then you can play with it by atomic substitution or by strain engineering using nanotechnology, or you can simply take almost any material and try to make it multiferroic by ultrafast light pulses. And this actually can be done at room temperature and making it easier for further applications. So with this, I'd like to thank you for your time and I'm open for questions.
Thank you, Rui. There's already a question on the chat, so I'll allow you to unmute yourself, Himanshu. And we only have time for like 2 questions, 3 if the third one is big.
Hello.
Go ahead,
The
Himanshu.
question is, what method did you use to deposit the confirm of GDMNO3 on the SRTiO3 substrate?
It was a pulse laser deposition, so PLD. And we deposit.
What was the thickness of the film?
Sorry?
The thickness of the film.
Deposited.
The thickness, yes. The thickness was around 30 nanometers. So above that, the strain relaxes and the structure becomes more bulk-like. So below 30 nanometers, you have a fully strained epitaxial film.
What are the applications? As you said, there are applications, but they are rare. So what are those applications?
At low temperatures, it's not so easy, but at high temperatures, like I said, if you have a multiferroic material, you can you can use the electric field to change the magnetic properties, and all our memories are based on magnetic properties, magnetic domains, magnetic memories, and if you can change them with electric field, it's much better. Besides that, you also can do like magnetic tunnel junctions, but multiferroic tunnel junctions, where you can also control with electric field, or even exchange bias, multiferroic exchange bias applications for having, again, logic states with 4 parameters and mainly controllable by electric field.
So when you apply this terahertz pulse, does it also affect the substrate? Substrate also plays a role in the study, or it does not, other than causing the strain?
I mean, about what is the effect of the substrate? Yeah, the substrate was chosen in order to provoke induce those that strain that you need for this case the gadolinium manganite to become ferroelectric. So of course, if you choose another substrate, this will not occur in this way.
Other than causing
Sorry, Himanshu, we don't have more. Sorry, we don't have time for more questions. If you want, you can write your email on the chat if you're okay with that. And Himanshu, you can write an email to Rui, because we need to move on to our next speaker.
Okay, no problem.
Sorry, thank you so much. Thank you so much. Thank you, Rui. So our next speaker is Célia Sousa. Célia, you should be able to share your screen.
Yes, thank you, Sophia.
Perfect.
Okay, thank you. Hello, everyone. First of all, congratulations to the organizers for this nice event. And I have also to acknowledge to the organizers for the invitation to present here a little bit more about the work that we are developing at IFIMUP. So as João Pedro presented before, we have 4 main research vectors in our institute, and my presentation today will be focused in my research line that is included in the IFIMUP Bio research line. So, as João Pedro explained in the first talk regarding the research at our institute, the research in this line is divided in 2 main topics: the use of spectroscopies, namely Raman and ultrafast laser spectroscopies for imaging, namely imaging of cancer. Now we are also combining the imaging by using a femtosecond laser with the plasmonic nanoparticles for phototherapy of cancer. And regarding the nanomaterials, we are using plasmonic nanomaterials, piezoelectric nanomaterials, and also magnetic materials for diagnosis and treatment of cancer diseases. So my talk today will be focused on the use of development and use of plasmonic and magnetic materials for cancer treatment. As you know, the conventional therapies used for cancer therapy, namely radiotherapy or hormonal therapies or targeted therapies, have a limited efficacy due to the lack of cancer cells specificity. And nanotechnology can be a good alternative to treat the cancer diseases. So nowadays we are able to control the size, the shape, and the type of materials that we can include in a nanoparticle, and we can also play with the surface functionalization. So in order to target our nanoparticles to the desired part of the body that we want to treat. And this is not only my opinion, that physicists are needed in this field of medicine. For example, by using this kind of magnetic and plasmonic nanoparticles, we can combine therapy and diagnosis at the same time, the called theragnosis techniques. For example, we can use the nanoparticles for phototherapy or for controlled drug delivery, and at the same time perform diagnosis. For example, in the case of magnetic nanoparticles, they are also good contrast agents in MRI or for other new imaging techniques. So the use of nanoparticles in medicine, it's not a dream, it's already a reality, and there are several nanoformulations in the market. For example, Doxil is a nanoformulation based in a liposome that have inside a drug called doxorubicin that is used in several types of, in the treatment of several types of cancer, namely breast cancer. And but Doxil is not have a very good results when compared with the free drug formulation. However, Doxil is not the first line of cancer treatment due to the high costs of this nanoformulation. Another example that I want to show you is the nanotherm. Nanotherm is another nanoformulation based on superparamagnetic iron oxide nanoparticles for hyperthermia treatment of cancer that is being applied in several types of tumors in clinical trials. However, the use of nanotherm for nanoformulation is limited due to the high concentration of particles needed to an efficient treatment, as well as high magnetic fields and frequencies. So our strategy is to develop new types of plasmonic and magnetic nanoparticles, biocompatible and efficient nanoparticles that will be a core of the nanoparticle, and then as a shell of the nanoparticle we are using lipid nanoparticles. Inside these lipid nano carriers we can put the magnetic or plasmonic nanoparticles and also some drugs. So what we are developing is a shell, a lipid shell, where we can put inside magnetic nanoparticles, plasmonic nanoparticles, also drugs, and you can also functionalize the surface of these nanoparticles with a target to deliver the drugs and deliver the treatment and perform the imaging in a specific region of the body. So we will use two main physical mechanisms to promote the drug release and perform the cell death. One of them is the called magnetomechanical induced cell damage. So instead of magnetic hyperthermia that is based in an increase of the local increase of the temperature, in the case of this treatment, we use magnetic nanodiscs that are in spin vortex ground state, and by applying small or low magnetic fields and low frequencies, we are able to move our nanodiscs, and this magnetomechanical movement will induce the apoptosis of the cell. In principle, one disc per cell will be enough to induce the cell death. So compared with the superparamagnetic nanoparticles used in magnetic fluidic hyperthermia, we can perform a treatment with low frequencies, low magnetic fields, and very low concentrations when compared with the state-of-the-art techniques. On the other hand, we can use the plasmonic nanoparticles for plasmonic hyperthermia or phototherapy. We will combine our plasmonic nanoparticles with a laser. We are working with two types of lasers, continuous lasers and femtosecond lasers. And by irradiating these nanoparticles with a laser in a near infrared region where our body is transparent to the light, we are able to eat these nanoparticles and promote the drug release, the drug that are inside the lipid shell. The lipid shell will be broken and the drug will be released locally. Also, if we achieve temperatures higher than 42 degrees, we are also able to perform the phototherapy of the cells. Comparing spherical and high aspect ratio nanoparticles, we can see that high aspect ratio nanoparticles like nanowires, nanorods, or nanotubes present several advantages regarding the high surface area, the ability to tune the physical properties, and this kind of nanostructures also have a persisted circulation in our body. On the other hand, we also have to take into account the accumulation of therapeutics, and that is mainly determined by the size of the nanoparticles, their shape, but we can also play with the surface charge of the nanoparticles in order to reduce the accumulation of these nanotherapeutics. So, to grow our magnetic and plasmonic nanostructures, we use a template-assisted method. We start to oxidize an aluminum foil, and in specific conditions, we obtain aluminum oxide, a nanoporous aluminum membrane with pores where we can control the diameter and the length of these pores to have the desired dimensions. Then we can fill these pores with the desired material and grow inside these pores our high aspect ratio nanostructures. We can change the dimensions of our nanostructures from nanodiscs, as you can see here, and to nanowires with a high aspect ratio. So by playing with the dimensions of these nanostructures, we can also tune the magnetic properties. We can go from high aspect ratio nanostructures, where the magnetization is mainly dominated by the shape and isotropy, until to isotropic nanodiscs, or even for small nanostructures, we can achieve the superparamagnetic state. We can also combine different materials in the same nanowire. For example, here we have a nanowire with a magnetic and a plasmonic part. These kind of nanostructures can be used for magnetic hyperthermia or magnetomechanical cell death, combined with near hyperthermia, since we also have a plasmonic material in our nanowire. Also, both materials can be functionalized with the different molecules in the surface. So after the materials growth, we perform the cell viability of our nanostructures in order to determine the biocompatibility and the internalization of our nanoparticles by cancer cells. For example, so here you have an example for iron gold nanodiscs, and we can see that we have good biocompatibility of our nanodiscs, up to 120 discs per cell, and we can also achieve internalization of these nanostructures up to 120 discs per cell. And as I said before, for example, for magnetomechanical cell death applications, in principle, one disc or very low concentrations of discs are enough to perform an efficient treatment. Another example that I want to share with you is about lipidic nanostructures. So we recently developed a nanostructured lipid nanoparticle that will be the shell for the magnetic and plasmonic nanoparticles. And we encapsulated a drug, the doxorubicin, inside these lipid nanostructures. Our in vitro tests showed that these developed nanoparticles have potential application in breast cancer therapy, and they can be administered by oral administration. That is the best way to administrate the drugs. So finally, I have to acknowledge a lot of people and several national and international institutions that are in collaborating with us to develop these interdisciplinary work. So thank you very much for your attention. Your questions.
Thank you, Célia. We have time only for a very quick question. I will ask you if you want to write your email on the chat so that if someone asks
Yes,
questions,
of course, I will write
because
here
we
my
are really
email
running
on
out
the
of time.
chat.
So only if it is a very quick question. I believe no one has a quick question. Hopefully you have a long question. So thank you so much, Célia, Anna, and Rui. Thank you so much to IFIMUP for presenting itself.